Swayam Prabha. Digital India. Educated India.
So, last class we looked at the muscle structure and then the length tension relationship for the muscle at the sarcomere level. The sarcomere is the individual unit that is responsible for the contraction in the muscle. So, the muscle of course is not just the sarcomere is the contractile component, but there are other, there is connective tissue surrounding the muscle, there is also the tendon which actually transmits the force generated by the muscle to the bone. And so, those also influence the relationship of the force transmission. And so, today in this class we will look at some of those factors. So, the whole muscle behavior will also be influenced by those relationships. So, if you look at tendon characteristics, essentially the tendon serves to transmit the force of the associated muscle to the bone. They are pretty powerful. Tendons are they carry large loads, they have and their characteristics. So, they tend to be viscoelastic. So, tendons are viscoelastic structures. Which means they exhibit both viscous and elastic behavior. So, but it is and they are linear in their stress strain relationship. So, tendons can store energy, they are elastic, but they also exhibit hysteresis. Generally tend to resist stretch and are quite flexible, because in the body they have to move like more strips, and they could be different cross sections. You could have circular, oval or flat shapes for the tendons. And tendons are basically a bunch of inelastic fibers, but the fibers in the relaxed state are kind of wavy, they are slack and wavy. So, if you have this and you have the fibers with this is a, if you look at the fibers in the tendons, they tend to be like that, they tend to be wavy. Okay. So, when force is applied initially, they tend to stretch. So, this also influences. So, when a tendon is stretched, these fibers straighten out, right. Relaxed state, and this is the stretched state. And because they are viscoelastic, their behavior is time dependent. So, you load it very quickly, okay, it will exhibit greater resistance. Okay. So, those are some of the characteristics of the tendon that will also influence the overall muscle behavior. So, if you look at force versus time, force that is transmitted versus the time, you will see that initially because of the slack in the tendon, the force transmission is low to the bone, and then the force increases linearly and then levels out. So, when you look at the muscle force over time, initially because of the non-linear nature of the tendon, you have, it takes time to develop force, and then once it is stretched out, now it is trying to stretch it even further, and that has to do with the properties of the tissue and not so much this structural aspect of the waviness of the fibers. So, now you are starting to pull on the straight fibers, and that part of the force transmission tends to be linear with time, and then it sort of levels off after a point.
We are applying force at the tendons first and then it is transmitting the muscles and then.
Now, the muscle is the contractile, the muscle is what is generating the force. The muscle generates the force, the tendon first, like a spring, it kind of straightens out, and then it is able to transmit the force to the bone that to which it is attached. Okay. So, there are this model. So, if you look at the whole muscle, force versus the lengthening. So, this is for the individual sarcomere, right. If you look at the whole muscle, you will see that somewhere close to the again the resting length, let us call this the resting length, is where you will see the maximum force developed in the muscle. So, this is the force generated by the muscle. Okay. So, this is the contractile component of the force that is generated, and similar to in the sarcomere case, you will see that if it is shorter than the resting length, then it tends to spot in between where close to the resting length, where you see the maximum force production in the actuator, the muscle, the contractile component. Now, if you look at the elastic tissues, okay, the connective tissue, you have tissue surrounding the muscle, you have the tendon. So, these are called the passive components, passive elastic components. So, the connective tissue around the muscle, epimysium and all those tissues surrounding the muscle, and then the tendons, because they cannot generate force. Okay. So, they are called the passive elastic components, and the muscle is your active component. So, this blue is your active component, muscle's active component. Component due to the muscle's contractibility. Okay. Now, if you look at the passive elastic components, what happens is they start as the muscle is past its resting length, they start acting, because now you are stretching these tissues. Okay. So, they start developing force because of the stretch. When the muscle is below its resting length, you do not really have much of an effect of the passive components. Okay. But with, because once what you see is how much, whatever force is generated by the muscle is transmitted to the bone. Okay. So, the net, if you look at the net force, then initially it is just, it follows the contractile component, and then because it is basically the sum of these two. This is the net force that is transmitted to the bone. So, the passive elastic components start contributing more once the muscle is past its resting length.
That means that is become active component.
That, I am sorry, that becomes
Active component, right?
passive. It is only because of the stretch. Okay, you do not call a spring an actuator. Okay, it is whereas the muscle is producing the force. It is a resistive force. It is a response.
Force is not generated because of stretching.
Because of stretching, it is generated. Yes.
Force which is generated due to stretching is part of the muscle force, right? So why are we adding the two?
No. So, when I talk about the blue one, I am talking about only the contractile force that is generated by the muscle, by the muscle's active component. That is why I am adding. So, you have tension generated by the muscle. Now, you are also stretching some additional tissues that are attached to that muscle. Okay, that additional force is because of these passive elastic components.
Is it getting induced in the connective tissue? Like you're adding.
Because it is a response to an applied stretch.
Spring is mounted at one end and the other end is connected to an actuator. You're
Yes.
pulling that actuator. So in a sense you are just transmitting the force, right, from the actuator to the wall where the spring is mounted.
True, but beyond a point, when you stretch this beyond that. Okay, so initially that is why in the, when the muscle is just in the contracted state, on the left side of this graph you see slack. Okay, you do not have a contribution to the tension from the passive components. It is only when they are stretched that they start,
Muscle.
it is transferring it to the bones of the body. The additional force is the resistance of this. So, you have let us see, this is like a flexible but rather inextensible cable, right, that tendon is like that. Okay. You are pulling on it with a force. Okay, that is the muscle is generating a force which is pulling on this. Now, when this starts, black line is. So, if you are at the, you saw with the sarcomere that when it is past the resting length, the force drops off, right. So, after a point you can't even apply the contractive force, but you still have resistance. That resistance is only due to the passive elastic component. So, you see here after it drops off, the two meet, the net force is only due to the.
In the case of when the muscle is contracted without generating any tension in the tendons, how is it transmitting it?
It is transmitting. So, its contribution is minimal at that point, it is contributing.
But it's in tension.
So, if it is not stretched beyond, so it straightens out and transmits the force to that. Now, you start stretching it even further, then it starts resisting that stretch. Okay. Because it is at the molecular level, now the material is reacting to the force that is applied to it. So, we can model this muscle and the tendon and the connective tissue. So, one of the objectives of any time as engineers, we try to approximate something with a model. So, approximate behavior with a model. So, we can create, so Hill came up with this model for a muscle, and that has, and it is known as Hill's muscle model. The muscle, the whole muscle. So, this is for the musculotendinous unit, it is for the entire muscle plus tendon. So, the muscle tendon unit can be modeled using these elements, where this CC component, the contractile component, and it represents the muscle, the actuator, which is generating the force. Then you have the contractile component is in series with the tendon. You can think of it in terms of, it is in series with, so it is called the series elastic component. Wait a minute. Yeah, okay. And P is the parallel elastic component. So, these are the tissues. Okay. So, you have whatever force generated by the muscle, and then that is the same force experienced by the tendon. Okay. The tendon and the muscle experience the same forces because they are in series, and then you have the parallel elastic, it is in parallel to this system of the muscle and the tendon, and that is your connective tissue. So, that is your parallel elastic component. So, when you model and you want to represent muscles, this is one of the most common models used to represent the muscle, and it is called the Hill's muscle model. In some places you will also see a slightly different form of this. Where you have PEC, okay, and then you have the SCC. So, this represents the structure more closely. You have the contractile component, you have the passive, and then you have the SCC. But typically the contribution of the PEC is lower. So, both types of models are used for modeling the muscle behavior. Okay. Now, we will look at so before we do that, let us look at this. When do we experience this? Okay, this passive and active tension, and when does it make a difference? When do we operate? In most normal activities, we will be operating in the central zone. Okay. But there are times where you will in some muscles you will find that we operate at the extremes. Okay. So, biarticular muscles where the passive tension starts to make a difference. Okay. So, the biarticular muscles cross two joints. So, most muscle joints. So, they influence in these cases the passive tension that we saw starts playing a role. This passive tension starts playing a role, and I will explain it with an example. And also you start operating at the two extremes of this curve. Okay. So, let us see. So, if the muscle, so a biarticular muscle crosses two joints, your finger flexors. Okay. They flex both your wrist. So, they cross them here and sort of fans out, the tendons fan out to the fingers. So, when my wrist is in the neutral position, okay, so they are crossing both, I can get a pretty good grip. Okay, I can contract my muscles and grip something pretty hard. Okay. Now, suppose I also flex my wrist. Flex your wrist. So, grip something, then flex your wrist. As you increase your flexion, what happens? You start losing your grip, because now the muscle has shortened beyond its resting length. So, its ability to generate force has now gone down. Okay, because you know when you are flexing it, this muscle is contracting. So, I am not able to generate maximum flexion in both the joints by so this case is called active insufficiency. Sorry about that. So, what it means is two joint muscles or biarticular muscles, muscles that cross two joints cannot across if you are lying face down, okay, when you are same thing happens. Another set of muscles, so this is at the finger and wrist flexors, right. This is an example. Example of active insufficiency. Another example are your hamstrings. If you are lying face down, okay, hamstrings flex the knee. Okay. Hamstrings are the muscles at the back of your leg. When they contract, your knee flexes. So, if my knee is flexed, the hamstrings also cross the hip, then I can't extend my knee fully. Sorry, I can't extend my hip fully, because the hamstrings also extend the hip, move the hip back, move the thigh back. Okay. So, again that is an example of active insufficiency, because the hamstrings are already in a shortened position. So, if your knee is flexed, so I can do this when my knee is extended, I can extend my hip farther, okay. But if my knee is flexed, then you will feel the tightness, you will not be able to extend it farther. Okay. So, the hamstrings with knee flexion, so hip extension is limited, when knee is flexed. So, actively I can't extend my hip when my knee is flexed. The other situation, that is where the passive tension starts playing a role, is called passive insufficiency. Again you see this with muscles that cross the two joints, because that is when you can get them to operate at the more extreme positions. So, if you look at passive insufficiency, then joints at the same time, again muscles. Again you can use the hamstrings as an example. So, now you are stretching the hamstrings. Okay. So, you lie down, okay, in the supine position on your back. you lie down on your back and you start lifting your leg. You are flexing your hip, try not to bend your knee. Okay? You are lifting, you are keeping your leg straight and you are lifting your leg at the hip. Okay? Now, what are you doing? You are stretching the hamstrings. Okay, as I said, so the hamstring is lengthened and you are lifting your leg. What happens? Okay, unless you have very hamstrings, right? Because it is the tissue now that is providing the tension, providing the resistance. The passive tension is coming into play. It does not matter how much you try to, it is not your the contractile component that is playing a part as much as it is the passive tension. So, this is called passive insufficiency because it is playing a role, passive component of the muscle that is playing a role. Okay. So, these happen with the biarticular joints. So, other biarticular muscles are, so some examples of biarticular muscles, and you can try some of these. Try experiencing the passive and the active insufficiency. So, you have the hamstrings, you have the rectus femoris which belongs to the quadriceps, you have the gastrocnemius muscle which is your calf muscle that crosses the ankle and the knee. These two cross the hip and the knee, the hamstrings and the rectus femoris. The gastrocnemius crosses the knee and the ankle. And the flexors and extensors of the hand. Which cross the wrist and several fingers. So, these are muscles over which you can experience the extremes of the length tension relationship of the muscle and surrounding tissue. Okay. Okay. Some more terminology with respect to muscles. We talk about the origin. So, a muscle is typically attached to two bones. Okay. We talk about the origin. So, the muscle is attached to a bone at both ends. So, the more proximal attachment or the attachment closer to the midline of the body. So, the proximal distal, remember we talk about it in terms of the appendicular skeleton, right, or closer to the middle of the body, you call it the origin. That is called the origin of the muscle. The other end is called the insertion. So, the attachment that is distal or farther from the midline is called the insertion. And usually this is where it converges to a tendon and inserts, because trying to make. So, the insertion usually converges, the muscle converges to a tendon, and then you have your point of insertion in the bone. So, more than one attachment site is always possible at both ends, and the muscle can move either bone in most cases.
The insertion is muscle to tendon or tendon to bone?
Tendon to bone, yeah, that end where it attaches, the distal place where it attaches. The muscle, only in a few cases it attaches directly to the bone, usually it is through a tendon. So, it is the location we are talking about here. So, wherever the more proximal or closer to the midline, that is your origin, it is called the muscle origin. It is understood that it is typically it is the tendon that is inserting into the bone. Okay. So, we talk about, but we say because it is the muscle action, we talk about it as the muscle's insertion, muscle's origin, muscle's insertion. Okay. So, if you look at, for instance, so the muscle can move either of the bones. You have two bones connected by a joint. The muscle can move either bone. There is nothing that says that only one bone is movable. What happens usually is that other muscles or other things come into play at one end to kind of stabilize that bone, and so you have movement of the other bone. Okay.